Hello. So, many years ago, I read the play Hapgood by Tom Stoppard. He's one of my favorite playwrights, and he likes to use a lot of really complex thoughts and ideas in his plays. He loves to play around with any sort of concept that's hard. And Hapgood is a spy story. It's set during the Cold War, and they're trying to figure out who the double agent is. But he sets it in the world of quantum physics, and the first time I read it, quite frankly, I thought it was brilliantly written, but I had no clue what was going on a lot of the time, which is common for reading a lot of Tom Stoppard plays. But now, using what we learned in class about wave functions and the uncertainty principles and quantum mechanics, I feel that I understand the play better now, having reread it and thought through it in an academic fashion, and I'm going to explain how that helped. One of the continuous schemes in this is they keep modeling their agents as particles, as electrons especially, and they keep talking about them in terms of that. So the thing that I really get this time that I definitely didn't get before is if you're thinking of them as electrons and not people, that means that the classical rules of physics don't apply, and therefore all the classical ideas that I kept getting confused about, going, wait, that doesn't make sense in the real world. Well, it's the real world, yes, but it's a specific subset of the real world where different rules apply. And he uses quantum physics as an analog for the lives that spies live being so divorced from what normal people experience that it seems crazy and out there, but it's still true, it's still real, and that parallels the difference between classical and quantum physics. They both apply, but they're hard to cross over between. And one thing they do is they talk about how you don't know whether someone is on your side or their side until you check. And the whole plot gets started off when they set up an experiment to basically they describe it as interrogating the agent to see if he is a wave function or a particle. And they talk about how the one guy, he says, I don't even know what side I'm on until there's an interrogation, because you can't divorce for light, you can't divorce the wave function and the wave form of light from the particle form of light. It's sometimes one sometimes shows up as the other, but until you check, it's intrinsically both, and that is a major theme throughout the play. Indeed, they actually figure out how the double agent Ridley was able to do this. It only makes sense if you consider him as an electron and not a human. For one thing, there's twins, and the whole idea that everyone has twins and that there's two of everyone is incredibly thorough. It goes throughout the play, and I found that really confusing the first time I read it. He says, and Kenner, who's the physicist in the play, says, you analyzes it to plus or minus square root. There's two correct answers. Are they, you look at me and think, which is he, plus or minus? If only you could figure it out, like looking into me to find my root. And then you still wouldn't know. We're all doubles. And that, I think, is an analog for electron spin, whether they're spin up or spin down. Well, that depends on the axis. And depending on how you look at it, it can even change considering exactly what you know. There's always this inherent duality to every particle and to every spy. They're inherently on both sides, and you can only check at certain discrete times which is which, and you can only know a little about them at a time, and you lose some of what you know by finding other things out. And that whole idea is very important because there's a complicated briefcase switch at the beginning due to their original probing technique, and it is only possible for that pattern to happen if there were two people instead of one, which is because you can't tell which electron is which. They're indistinguishable, therefore one is as good as the other, and you can't inherently know which is which. And that also ties into not knowing which twin is which of either the Russian twins or the Ridley twins, or when Hapgood may or may not have a sister. I'm never sure by the end if she's actually twins or not, or pretending to be twins. And then they also talk about how in the briefcase their tracking device gets taken out, but they should have known if the briefcase had been opened, and they should not have been able to switch what was in there. And then they talk about how that happens is because they can't know where Ridley is and what he's doing at the same time, which in a classical sense makes no sense whatsoever, because you think if you know where he is, then you've got to be able to see him and then you can see what he's doing. But if you consider him as an electron and as the equivalent of momentum and position in the Heisenberg uncertainty principle, then it makes complete sense. They even talk about that in the play, but I didn't really understand a lot of Kenner's long monologues about physics the first time I read it. He says, it defeats surveillance because when you know what it's doing, you can't be certain what it is. And when you know where it is, you can't be certain what it's doing. Heisenberg's uncertainty principle, and this is not because you're not looking carefully enough. It is because there is no such thing as an electron with a definite position and definite momentum. You fix one, you lose the other, and it's all done without tricks. It's the real world. It is awake. And so the only way that Ridley could possibly have switched the tracking device, which we know happens because they find the proof, is if we model him as an electron, and therefore at the moments when we know where he is, we can't know what he is doing, because his when you know where he is, his wave function collapses into a specific eigen state, which is just a long spike of certainty, yet the wave function is related to momentum by lambda equals h over p. And so if you have a definite momentum, you have a definite wavelength, and you can't have a definite wavelength and be only one infinite spike. They just don't go together. And that's how Ridley was able to solve it. And there's also, thinking of wave functions and probability again, there's also one scene which is just described even as an interscene. And it is very weird. It just says, Hapgood leaves the room. Ridley stays where he is. The next time he moves, he's somebody else. So we lose the last set without losing Ridley. When the set is gone, he is in some different place. And it makes no sense. It just flows through this place. And he somehow gets from her apartment to somewhere. It's not even clear where it is. It's just somewhere else. The stage directions say anywhere else, without having been anywhere in between. And that is analogous to quantum tunneling, and it even mentions that in the stage directions. It's like a quantum jump. And that happens because, I'd heard of it happening before, I just had no idea why. It happens because when you have your allowable eigenfunction for your energy vectors, and you've got the forbidden zones, the tail in the forbidden zones doesn't just drop down immediately. It kind of waves down, and there's a little bit under it, so there's still a teeny probability of finding it where it can't be and where it shouldn't have gotten through. And yet that can happen, and it does happen in here, modeling Ridley as an electron. So honestly, after reading this play again, I feel like I understand it so much more, and I understand what he's talking about specifically scientifically, as well as what he's trying to do literarily, rather than just thinking of it as an interesting story.